Before we get into section 12.6, I think it would be helpful if we quickly reviewed some conic sections. Conic sections are going to be used to a certain extent in the graphs of some of these surfaces that we're going to talk about today. So really just two conic sections that I'd like to talk about. The graph of an ellipse. You might recall that you could have something of the form x squared over a squared plus y squared over b squared equals 1. Well, this a term, not the squared term itself, but like in this case right here, this is 2 squared. This would indicate that, of course, we'd have a center at 0, 0 here. I hope we recall that from our days in pre-calc. But down below, seeing a 2 squared would indicate that we'd move 2 steps to the left, 2 steps to the right of our center. Down below with this y squared having a 9 below, that's 3 squared. That means that up from our center we'd move 3 steps. Likewise, we'd also move 3 down. And this would be our oval. It's an ellipse, forgive the sloppiness. Obviously, if our a and b terms are to be equal, we'd actually have a circle. But that's an ellipse. You'd always see an addition of these squared terms. Very likely your longer axis, called your major axis, that definitely could be going in a horizontal direction if your a term is larger. Now, when you're talking about a hyperbola, though, a hyperbola, you're always going to see some subtractions. So let's just say that I gave you x squared all over a squared minus y squared over b squared equals 1. Just writing very generally right now, I'm not even doing a specific numeric example. I'd move a steps to the right, a steps to the left of my center. Again, I'm at 0, 0. I'd move b steps up and b steps below. You might remember we made ourselves a little box, a little rectangle, and the diagonals of that would be the asymptotes of our hyperbola. But what I most want to review with you, most importantly, is that the positive term, this positive term indicates the direction that the hyperbola would open. If x squared over a squared is the positive term, then we'd open up in the x direction. Likewise, if we had y squared over a squared, well, you might get the idea that very quickly, cutting to the chase, we'd get a graph that looks something like this. Of course, we'd be moving b steps up, b steps down. We'd move a steps to the left, a steps to the right, and of course we'd have our little box. But most importantly, I just wanted you to know that the positive term indicates the direction of which the hyperbola opens. Well, that being said, let's jump into today's lesson. It's a longer lesson. The next day on it will be extremely short, giving us a lot of time to review. Let's talk about cylinders. In geometry, a cylinder is a three-dimensional object where you have two bases being circles and a lateral surface, a smooth surface around the shape between. And of course, we've talked about that many years ago in geometry. Well, now in multivariable calculus, we're going to see that this cylinder could look like this, but we're going to expand on this definition. We're going to say, look, it is a surface composed of all lines, which we're going to call rulings, passing through a plane curve, a curve that could be a circle, an ellipse, a parabola, a hyperbola, and all these lines that would be parallel to a given line. So, if I may, let's just start off and say that in a plane we have, say, a parabola that's opening sideways. what we're seeing is we would want to have other parabolas like so. And what we'd see is that if we'd connect them all with straight lines, these are the rulings. A ruling passing through a plane curve that would be parallel to a given line. Maybe this red line is the given line. If we drew every possible line that we could parallel to that line, well, my goodness, you could see what would happen. All of a sudden, you'd get this definite surface. You could bend a piece of paper, fold it into this kind of a parabolic shape. We would call this a cylinder. The curve would be a generating curve. We would get a parabola as the generating curve. Obviously, in the traditional cylinder, the generating curve would be a circle. You could really think of it in the same way if you'd like. You could see rulings here just as well. Lines parallel to a given line, whatever line you'd like to draw in there. So that's where we're going. We're going to very quickly graph some cylinders. Let's sketch z equals y squared. And of course, the big difference here is now we are definitely going to graph in 3 dimensions. And of course, you can see that we've got a x, y, z axis. I think most notable when we look at this, we're going to notice that there is no x term. When a variable is absent, we could actually talk about something called a trace. A trace is going to be a 2-dimensional snapshot of the curve. If I talk about the YZ trace, this means we're assuming that x is equal to 0. Of course, there is no x in this equation to begin with, so really this equation would be exactly the same for this trace, the YZ trace. In the future, if we had an x term, for example, if we would have said plus x or something like that, the trace would allow that x value to be 0 and effectively disappear. But if we just went to 2D, and if we were looking at this where our dependent and independent variables are going to be, as I'm writing here, the independent variable would be y, and our dependent variable would be z. Normally, we would write a parabola like y equals x squared. X squared would be on the x-axis, of course. Well, x terms are measured independently. The y value, of course, would be on the vertical axis. Y is depending on x. We get our y value after we do some work with this x value. You could see a definite parallel here. So if I gave you z equals y squared, you'd say, well, my goodness, wouldn't that just look like an ordinary parabola that we've seen? And then wouldn't this just simply be with these different axes? Indeed, that's true. What I'd like to show you is that we could very quickly make a sketch as to what's happening here. Look, if x is equal to 0, it's as if we just had the z and the y-axis in the picture. We could make this little parabola just like so. Okay, so imagine that the x-axis, you could even erase everything that you'd see. That's more or less what our graph would look like. But remember, x could be all different types of values, whether x was 5, whether x was 10. No matter what x value you'd choose, you would get a parabola. It would look something like this. You could let x be something negative, and of course it would go just like so. So what we're seeing, guys, is we could connect some rulings here. We could make some lines like on the top and on the bottom here. It's going to be as if we took a piece of paper and just folded it. Sometimes kids like to draw in a few rulings, and you certainly may. These can be hard to draw, but we're just going to have a pretty good sketch as to what's happening. On a test, I'm not really super concerned with actual pictures being drawn. We're going to talk more about that in the future. But look, your calculator can be of some help. We can definitely get some help here. Let's go to mode. And pressing mode, graph, hit the right arrow and go down to 3D. You've got to hit enter. And then you have to hit enter again. You know, you'll just notice that it's been selected as 3D, but you have to hit enter to save it. Then we want to go to y equals. Now y equals is right above the F1 key. Hit green diamond and then hit y equals. We'll say z equals y. Now the y is 2 buttons above the 7. Hit the caret button, it's right above divide, and then hit a 2. Hit enter. Of course, it's not graphed. To graph, look up at F3, this button right at the top row. Hit green diamond, F3, and it's going to take a little while to calculate this. It's going to be a lot of work behind the scene to let you know they've graphed a whole bunch of parabolas that would look something like this. Sometimes the TI-89 can be especially big help. Not always, I'm sad to say. Quickly, let's look at y squared plus z squared equals 1. Very quickly, kids can say, well, my goodness, this looks like we're in a z-y axis like before. There's no x-axis to speak of. I guess this is the equation of a circle with a radius of 1. And very quickly, kids would say, well, wait a minute, if that's the case, if this is really the equation of a circle with a radius of 1, how about we just go ahead and we make some circles, and we could say, well, you know, look at this, and you know what, I'm going to draw the z-axis going down. You know, you could even make this circle here dotted so that you can see that really we wouldn't be able to see all of that necessarily. You could say, well, look, we're going to have a circle out in front, and you know, here maybe you'd want to draw a ruling, draw another ruling, draw another circle maybe back here if you'd like. Very often kids are going to say, well, Mr. Dobner, isn't this really the traditional geometric cylinder? Indeed it is. You bet it is. I hate to tell you this, but the TI-89 doesn't always do a great job. You can see some guidelines here. You know, solving for z squared, you can't get two graphs to show up simultaneously on this 3D form here. So, you know, I said, you know, if you're solving here, you can read off to the side. You got to have two different solutions. The square root of 1 minus y squared. And tell you what, we'll just graph that alone. We're getting a little tight on time right now. But if we just hit graph right now, you can get a little disappointed. Because in all honesty, guys, you're going to see something rather obscure. It's not looking like what we just graphed here nice and quickly. By the way, you might remember even your 84 in the past years, it's had trouble graphing lines. You can say, wow, graphing circles. I'm so sorry. Right now, this appears to be a line. Obviously, we know this should be a circular cylinder. Look, you could do some zooming. Press F2 and hit zoom in and hit enter. And hit enter a second time, and it's going to regraph. You might want to even do this yet again. You're only going to get half of your curve, sadly. And it's not even going to look especially accurate. But if you zoomed in again, you could see what's happening. At least it could give you an idea. So these 89s aren't perfect, especially when z is squared. But at the very least, we're going to get some help. By the way, down here is the general equation that we're going to see. The XY, XZ, and YZ, these are rotations. We're not going to deal with that as much. We're going to keep talking with